Picture a universe so dark and silent that not a single star flickered in the endless void. No galaxies spinning their cosmic dances, no planets cradling life, just an infinite stretch of blackness, cold and untouched. This wasn't some distant nightmare or a scene from science fiction. It was real. For hundreds of millions of years after the Big Bang, the cosmos plunged into what scientists call the Dark Ages, a time so mysterious that even our most powerful telescopes struggle to pierce its secrets. But what if I told you that hidden within this ancient darkness lie clues that could rewrite everything we know about the birth of the universe? Today, we're diving into 30 of the most mind-bending theories about this enigmatic era. Some suggest the Dark Ages were anything but empty, teeming with exotic particles, phantom energies, or even the first stirrings of life itself. Others propose that this period holds the key to understanding dark matter, the multiverse, or forces we haven't even discovered yet. Imagine unlocking a cosmic puzzle where every piece reshapes our place in the grand tapestry of existence. That's the journey we're about to take together. So why does this shadowy chapter of the universe matter to us? Because buried in that darkness are the origins of everything, the raw materials of stars, planets, and ultimately us. The theories we'll explore aren't just wild guesses. They're the cutting edge of human curiosity, where astronomers and physicists grapple with questions that stretch the limits of imagination. By the end of this, you won't just see the Dark Ages as a blank spot in history. You'll see it as a frontier, one that's waiting to reveal its secrets and maybe, just maybe, show us glimpses of realities beyond our own. Ready to step into the unknown? Let's begin. The faint glow of the cosmic microwave background isn't just an echo of the Big Bang. It's a time capsule carrying whispers from the universe's darkest chapter. Picture this, a map of the entire sky, splashed with tiny variations in temperature, hotter and colder patches no bigger than 1/100th of a degree. These aren't random blips, they're cosmic fingerprints imprinted during the Dark Ages, and they might hold the keys to understanding what happened when the universe was just an infant, shrouded in perfect blackness. Take the infamous cold spot, for example. Stretching across a vast region of space, this mysterious chill in the CMB defies easy explanation. Some scientists think it could be a scar, a colossal void left behind by an ancient collision between our universe and another, a bubble from a parallel reality brushing against ours. Others argue it's evidence of exotic physics, like dark energy acting in ways we don't yet understand. Then there's the wildest idea of all, that it's a shadow cast by something even stranger, a structure so immense it warped space-time itself during the Dark Ages. But the cold spot isn't the only anomaly. Tiny twists in the CMB's polarization, the way its light waves wiggle, hint at forces at work during those primordial centuries. Maybe it was the first stirrings of dark matter clumping together, or the ghostly pull of quantum fluctuations frozen into the fabric of the cosmos. Simulations show that if we could decode these patterns with enough precision, we might even glimpse the birth of the very first proto-galaxies, their faint gravitational tugs subtly bending the CMB's light like ripples in a pond. What makes this so thrilling is that we're not just staring at static. These anomalies are puzzles waiting to be solved, each one a piece of the Dark Ages' hidden story. And with next-generation telescopes tuning into the CMB with unprecedented sharpness, we're on the verge of turning these whispers into shouts, finally hearing what the universe has been trying to tell us for over 13 billion years. What if the early universe wasn't just dark but crawling with black holes? Not the monstrous giants we picture today, but tiny, ancient ones, each no heavier than an asteroid and small enough to fit in your palm. These primordial black holes could have formed in the chaotic moments after the Big Bang, when random density fluctuations collapsed into microscopic points of infinite gravity. And here's the jaw-dropping part. These specks of darkness might have been so numerous that they were the universe's first scaffolding, shaping everything that came after. Think of them as cosmic seeds. While ordinary matter was still a diffuse soup of particles, these black holes could have clumped together first, their gravity pulling gas and dust into the earliest protogalaxies. Some scientists argue this would explain why we see galaxies forming so quickly in the cosmic record, far faster than traditional models predict. It's like finding a fully built city where there should only be a few scattered huts. Primordial black holes could be the missing architects, the invisible hands that sped up the universe's growth spurt. But the wildest twist, these ancient black holes might still be out there, lurking in the void as dark matter. Unlike hypothetical particles that have never been detected, primordial black holes are made of real, tangible gravity. They'd be nearly impossible to spot directly, drifting between stars without emitting light. Yet their shadows could bend distant starlight, or even trigger fleeting bursts of radiation as they evaporate over eons, leaving behind faint fingerprints. Of course, not everyone's convinced. Critics point out that if these black holes were everywhere, we'd expect to see more gravitational lensing effects or gaps in the cosmic microwave background. But supporters fire back. Maybe they're just the right size, too small to distort light dramatically, but massive enough to sculpt the cosmos. It's a cosmic detective story with stakes as vast as the universe itself. If primordial black holes are out there, they wouldn't just rewrite the history of the Dark Ages. They'd redefine what we call darkness altogether. While the universe slept in darkness, something invisible was already at work, pulling strings behind the cosmic curtain. Dark matter, that elusive substance outweighing ordinary matter 5-1, didn't just watch from the sidelines during the Dark Ages. It may have dictated them, slowing the birth of stars with its gravitational grip. Imagine a cosmic traffic jam, hydrogen gas eager to collapse into stars, kept circling in vast halos of dark matter like cars stuck on an endless roundabout. Without this shadowy scaffolding, the first stars might have ignited far sooner, but with it, the universe lingered in blackness for eons, the leading suspects. WIMP weakly interacting massive particles, the heavyweight champions of dark matter theories. These hypothetical particles barely talk to normal matter, only whispering through gravity. Yet their sheer abundance could have created vast wells in space-time, trapping gas so efficiently that it took hundreds of millions of years to clump enough for fusion to spark. Simulations show WIMP weaving a cosmic web so dense, it stifled star formation like a thick blanket smothering embers. But there's a rival theory that turns this picture upside down: actions. Unlike bulky WIMP, these ghostly particles could be billions of times lighter, behaving less like boulders in a river and more like a fine mist. If actions dominate, their quantum weirdness might have triggered bizarre effects during the Dark Ages, perhaps even forming Bose-Einstein condensates, ultra-cold puddles of dark matter that warped space itself. Some models suggest actions could have briefly lit up through rare interactions, casting faint glows in the void before vanishing again. Here's where it gets wild. Depending on which dark matter candidate is real, the Dark Ages might have unfolded in radically different ways. WIMP would have stretched the era into a long, cold wait, while actions could have peppered it with fleeting bursts of energy. And if neither is correct, that opens the door to even stranger possibilities like sterile neutrinos or hidden dimensions leaking gravitational echoes. The stakes couldn't be higher. Dark matter doesn't just explain why the universe stayed dark, it shapes how darkness gave way to light. Every galaxy we see today was born in the gravitational cradle of this mysterious substance. If we crack its identity, we'll do more than solve a cosmic whodunit. We'll rewrite the story of how our universe woke up. The early universe wasn't just dark, it was drowning in a sea of hydrogen so thick even light couldn't escape. Picture a cosmic swamp where every photon emitted by the first flickers of starlight got swallowed almost instantly by an ocean of neutral hydrogen atoms. These simple particles, just single protons paired with electrons, acted like a universal fog, soaking up ultraviolet radiation like a sponge. For nearly 100 million years, this hydrogen haze kept the universe locked in a state of eerie opacity, a twilight zone where nothing could shine through. But how does something as basic as hydrogen trap an entire universe in darkness? The answer lies in quantum mechanics. Neutral hydrogen atoms have a special quirk. Their electrons can absorb specific wavelengths of UV light, jumping to higher energy levels. In today's universe, this isn't a problem. Stars and galaxies constantly flood space with enough radiation to ionize hydrogen, stripping away those electrons and turning the gas transparent. Back then, though, the first stars hadn't yet fired up in earnest. The hydrogen simply sat there, cold and undisturbed, absorbing any feeble bursts of light that dared to pierce the gloom. Then came reionization, the universe's great awakening. As the first massive stars roared to life, their intense UV radiation began blasting apart hydrogen atoms, splitting them back into free protons and electrons. Imagine sunlight burning off morning mist, but on a scale spanning billions of light years. Over time, vast bubbles of ionized gas formed around these pioneer stars, growing and merging until the entire cosmic fog lifted. The universe, for the first time, became transparent. Here's where it gets fascinating. The timing and pattern of this reionization weren't uniform. Some regions cleared early, thanks to clusters of hot, bright stars, while others lagged behind, still shrouded in hydrogen's grip. This patchy process left scars we can still detect today, subtle ripples in the cosmic microwave background and distant quasars, whose light shows telltale absorption lines from the last pockets of lingering neutral hydrogen. What's truly mind-bending is that this hydrogen fog might have also shaped the very structure of galaxies. The resistance of neutral gas could have slowed the formation of early stars, forcing them to grow larger and hotter before they could punch through the haze. Some theorists even speculate that this prolonged struggle against the fog influenced the eventual distribution of galaxies, leaving voids and clusters in patterns we're still mapping. So the next time you gaze at the night sky, remember, the clear, star-filled expanse we see today was once an impenetrable murk, a relic of an era when the universe had to fight its way out of darkness atom by atom. And those ancient hydrogen atoms, they didn't just fade away, they became the raw fuel for everything that followed, the silent architects of the cosmic dawn. The universe's first stars might not have been the steady beacons we imagine instead. They could have flickered like candles in a cosmic wind, igniting and vanishing in quick succession. Recent simulations reveal a startling possibility. The early universe was so volatile that stars struggled to survive their own births, collapsing almost as quickly as they formed. This stop-and-start rhythm could explain why the Dark Ages dragged on for hundreds of millions of years longer than expected. Picture a newborn star in this primordial chaos. Without heavy elements to help it cool and stabilize, it would have grown massive and unstable, burning through its fuel at a furious pace. Some models suggest these pioneers lived fast and died young, exploding as supernova within just a few million years, their deaths flooding surrounding gas with turbulence. This chaos would have prevented new stars from forming nearby, creating pockets where darkness stubbornly held on. It's like trying to light a campfire in a hurricane. Every spark gets snuffed out before it can catch. But the plot thickens. Some of these early stars might not have died in dramatic explosions at all. Instead, they could have simply fizzled, collapsing directly into black holes without the cleansing blast of a supernova. Without that explosion to scatter heavy elements and clear the neighborhood, the gas around them would have remained too dense and hot for new stars to form, trapping entire regions in a cycle of false starts. Here's where simulations get eerie. When researchers account for these aborted stars, the timeline of cosmic dawn stretches out, matching the observed length of the dark ages more closely. The universe didn't just wake up, it hit the snooze button over and over, its early stars struggling against the very conditions that birthed them. Yet even these failures may have been essential. Each flicker, each collapse could have seeded the universe with the first black holes or sprinkled just enough heavy elements to pave the way for stable stars later on. What looks like a cosmic delay from our perspective might have been a necessary chaos, a messy rehearsal for the universe we know today. The Dark Ages weren't just empty, they were a stage where the first starlight stumbled before finding its footing. Hidden within the seemingly empty Dark Ages, an invisible force may have been shaping the universe's destiny. Magnetic fields so faint they'd struggle to lift a single grain of dust. These primordial strands of magnetism, weaker than the pull of a refrigerator magnet, could have woven through the cosmos like ghostly threads, guiding the collapse of gas into the first galaxies. It sounds improbable, but the evidence might be etched into the light of quasars billions of light years away. Think of these early magnetic fields as cosmic puppet strings. In a universe without stars or galaxies, even a feeble magnetic force could have nudged ionized gas into delicate filaments, creating pathways for matter to flow and clump. Simulations suggest that without these subtle influences, gas might have swirled chaotically, delaying star formation. But with magnetism at play, hydrogen could have aligned along these invisible lines, collapsing more efficiently into the seeds of future galaxies. The difference would have been microscopic at first, a slight preference for gas to move in one direction over another. But over millions of years, that tiny bias could have sculpted the large-scale structure of everything we see today. The proof: look to the light of ancient quasars. As their beams traveled through the early universe, they passed through clouds of intervening gas. If primordial magnetic fields existed, they'd have left subtle fingerprints on this light, specific patterns of polarization or faint twists in spectral lines. Astronomers have spotted tantalizing hints of such distortions in quasar light, as if the beams had brushed against something unseen. The challenge is distinguishing these signals from later magnetic interference, like cosmic static masking a whisper from the dawn of time. Critics argue that these signals could be noise or artifacts of later magnetic activity, but supporters point to a smoking gun: the sheer scale of magnetic fields observed in modern galaxies. They're too widespread and coherent to have formed solely after stars ignited. Like a fossil buried in space-time, primordial magnetism might be the only explanation for why even the emptiest voids between galaxies hum with faint magnetic energy. What's wildest is how these fields could have arisen. Some theories suggest they were born in the furious instants after the Big Bang, when quantum fluctuations spat out microscopic magnetic loops. Others propose they emerged during phase transitions in the early universe, like cracks forming in freezing ice but threaded with magnetism. If true, the Dark Ages weren't just a silent void. They were a canvas with invisible forces sketching the blueprint for all future light. Before the familiar constellations filled the sky, before the Milky Way even took shape, the universe birthed stars unlike anything we see today, colossal, furious beasts that burned blue hot and died young. These were population Roman 3 stars, the first generation of stellar giants, and they may have been hundreds of times more massive than our Sun. Picture a star so powerful that its surface temperature exceeded 100,000 degrees, screaming ultraviolet radiation into the void. These weren't just stars, they were cosmic demolition crews tearing through the Dark Ages with brute force and leaving behind the seeds of everything that followed. What made them so different? Pure hydrogen and helium. Without heavier elements to help regulate their internal pressure, these stars collapsed under their own gravity until nuclear fusion ignited with terrifying intensity. Their cores became furnaces of unimaginable heat, fusing elements at rates that would make modern stars seem like flickering candles. and because they lacked the coolant of metals, elements heavier than helium, they couldn't stabilize, burning through their fuel reserves in just a few million years. For comparison, our sun will shine for billions of years. Population Roman 3 stars lived fast, died violently, and in doing so, lit the fuse for cosmic evolution. Their deaths were just as important as their lives. When these monsters finally exploded as supernova, they didn't just fade away. They detonated with such force that they forged the universe's first heavy elements in their cores. Carbon, oxygen, even traces of iron sprayed into the surrounding gas, contaminating the pristine hydrogen clouds with the building blocks of planets and life. This was the universe's first act of recycling, turning the ashes of dead stars into the raw materials for everything to come. But here's the twist: some of these stars might not have exploded at all. Theoretical models suggest that the very largest population Roman 3 stars could have collapsed directly into black holes, vanishing without the enriching blast of a supernova. If true, pockets of the early universe might have remained metal-poor for longer, creating deserts where later stars struggled to form. It's a cosmic irony. The very stars that ended the Dark Ages may have also left behind shadows, regions where darkness clung stubbornly until later generations of stars finally filled the gaps. The legacy of these stellar titans is written in the oldest stars we can observe today. Deep in the outskirts of our galaxy, astronomers have found ancient stars with barely a trace of metals, relics from a time before the universe was polluted with stardust. These aging survivors are the closest thing we have to time capsules, holding chemical clues about their long-dead progenitors. By studying them, we're piecing together the biography of the universe's first starlight, the fire that burned away the Dark Ages and made the cosmos we know possible. Yet for all their impact, we've never directly seen a population Roman 3 star. They exist only in our theories and simulations, glimpsed through the forensic traces they left behind. That might change soon. Next-generation telescopes like the James Webb Space Telescope are scanning the deepest reaches of space and time, hunting for the telltale signature of these primordial giants. If we spot one, it won't just confirm a theory, it'll give us a front-row seat to the moment the universe woke up, when the first monsters of light roared against the darkness and changed everything. Dark energy isn't just shaping the universe's future. It might have left faint fingerprints in its deepest past. Most cosmologists assume this mysterious force only took charge recently, accelerating the expansion of space over the last few billion years. But what if its influence was quietly at work even during the Dark Ages, subtly tugging at the fabric of reality? The math tells a provocative story. If dark energy's strength has changed over time, its ghostly pressure could have left imprints on the cosmic microwave background or altered how quickly the first structures formed. Picture the early universe expanding in that primordial darkness, without galaxies or stars to mark the passage of time. Space itself stretched under competing influences, gravity pulling matter together, while dark energy, if present, pushed it apart. Today, dark energy overwhelms gravity, but back then, its effect would have been minuscule, like a single whisper in a hurricane. Yet even a whisper can ripple. Some models suggest that if dark energy's density fluctuated in the early universe, it might have created barely detectable variations in how matter clumped. Regions where it was slightly stronger could have expanded faster, delaying star formation, while weaker patches let gravity build proto-galaxies sooner. The evidence looked to the large-scale structure of today's universe. The distribution of galaxy clusters isn't perfectly uniform. Some voids are eerily empty, while filaments of matter weave complex webs. These patterns might encode echoes of dark energy's early activity. Simulations show that if dark energy interacted weakly with dark matter during the Dark Ages, it could have created bubbles of slightly faster expansion, leaving behind voids that later grew into the cosmic emptiness we observe. It's like finding fossilized air pockets in ancient rock. hints of forces at work before the mold was set. Then there's the cosmic microwave background's fine details. The CMB's temperature fluctuations are ultra-precise snapshots of the universe at 380,000 years old. If dark energy was already influencing spacetime's stretch, even minimally, it should have left subtle signatures in these patterns, perhaps a faint preference for certain scales of fluctuation. Researchers are scouring CMB data for anomalies, like a detective searching for smudges on a pristine photograph that shouldn't be there. Of course, not everyone's convinced. Skeptics argue that dark energy's current effects are so dominant that any early influence would have been drowned out. But proponents counter that the universe's history isn't binary, forces don't switch on abruptly. Just as a river's current begins with the first trickle, dark energy's push might have started as a quantum nudge, growing stronger as space emptied. The implications are staggering. If dark energy played even a tiny role in the Dark Ages, it reshapes our understanding of cosmic evolution. No longer just a late-stage actor, it becomes a character present from the opening scenes, a hidden hand that shaped the universe's story from the first moments of darkness to the glittering age of galaxies we see today. And if we can trace its whispers in the CMB or the voids between galaxies, we'll do more than solve a cosmic puzzle. We'll rewrite the timeline of everything. The universe's grand tapestry, galaxies clustered like glittering cities, vast voids stretching between them, might trace its origins to whispers smaller than atoms. At the dawn of time, when the cosmos was a seething quantum foam, microscopic fluctuations in energy flickered in and out of existence. These weren't just random blips. According to inflation theory, in the first fraction of a second after the Big Bang, space itself expanded faster than light, stretching those quantum ripples from subatomic scales to cosmic proportions. What began as quantum static became the blueprint for everything we see today. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, those dots grow into continents. Inflation did the same to quantum fluctuations, magnifying them into slight density variations across the young universe. Where these ripples were slightly denser, gravity pulled in more matter over billions of years, sculpting galaxies. Where they were fainter, voids remained. The cosmic microwave background captures this moment like a snapshot, those hot and cold spots. They're the stretched-out quantum seeds, frozen in time when the universe was just 380,000 years old. But here's where it gets wild. Without quantum mechanics' inherent randomness, the universe might have been unnervingly smooth. No stars, no planets, just a featureless soup of particles drifting in equilibrium. Inflation's genius was turning quantum chaos into cosmic order, transforming unpredictable flickers into the scaffolding for structure. Some models even suggest that these fluctuations weren't entirely random. Certain patterns in today's galaxy distribution hint at pre-inflation physics, like echoes of a deeper quantum reality that set the rules before spacetime as we know it existed. Critics argue that inflation's predictions are too flexible. It can explain almost any large-scale structure, making it hard to disprove, yet the math holds eerie precision. Simulations starting with quantum fluctuations and inflation reproduce the universe's filamentary web with uncanny accuracy, down to the statistical distribution of galaxy clusters. It's as if we've found the universe's recipe, written in the language of probabilities and space-time stretching. The profound implication: every galaxy, every nebula, even the emptiest reaches of space, owe their existence to quantum jitters so tiny they'd vanish in a heartbeat under normal conditions. The universe didn't just grow, it grew from something, a primordial instability woven into the fabric of reality itself. And if we could rewind far enough past the Dark Ages, past the first stars, we'd find that all structure, all complexity began as a whisper in the quantum dark. Simulations of the early universe paint a crowded picture. Thousands of dwarf galaxies swarming around larger ones like fireflies around a lantern. but when astronomers peer into the night sky, these tiny galaxies are conspicuously scarce. It's as if the cosmos lost its instruction manual for building small-scale structures, and the discrepancy has left scientists scratching their heads. This missing satellites problem isn't just a minor glitch, it threatens to upend our understanding of how galaxies form, and the Dark Ages might hold the key to solving it. The heart of the paradox lies in dark matter. According to our best models, the universe's invisible scaffolding should have funneled gas into countless small halos during the Dark Ages, each one a potential seed for a dwarf galaxy. Yet today, we see only a fraction of what simulations predict. Even stranger is the too big to fail problem. Some of these predicted halos are massive enough that they should have formed galaxies easily, yet they remain empty. It's like finding a fully equipped factory with no workers. Everything's in place, but nothing's being made. One leading theory suggests the Dark Ages weren't just dark, they were too dark. The first stars might have flooded the universe with such intense ultraviolet radiation that they sterilized small gas clouds before they could collapse into galaxies. Picture a cosmic blowtorch. UV photons could have heated hydrogen gas in these halos, keeping it too hot and diffused to form stars. Smaller halos with weaker gravity would have been especially vulnerable, their gas blasted away before it could ignite. This would explain why we see fewer dwarfs than expected. The smallest were literally vaporized in the cosmic dawn's harsh glare, but there's a twist. Some researchers argue the missing satellites aren't missing at all, they're just invisible. If these dwarf galaxies formed mostly dark matter with just a sprinkle of stars, they'd be nearly impossible to spot against the blackness of space. Recent surveys have uncovered ultra-faint dwarfs with so few stars that they're more shadow than substance, and there could be thousands more lurking undetected. The Dark Ages might have been a time of rampant galaxy formation, but with a catch: most were stillborn, their starlight snuffed out before it could shine. Another possibility: the rules of physics were different back then. If dark matter interacts with itself or with normal matter even slightly, it could have smoothed out small-scale clumps during the Dark Ages, preventing dwarf galaxies from forming. This warm or self-interacting dark matter would act less like invisible rocks and more like a subtle fluid, flowing away from regions where galaxies might have sprouted. The result: a universe with far fewer tiny galaxies than cold dark matter predicts. The implications are profound. If the missing satellites problem stems from the Dark Ages, it means this shadowy era didn't just passively host the birth of galaxies, it actively shaped which ones survived. Every galaxy we see today, from sprawling spirals to faint dwarfs, carries echoes of decisions made in that ancient darkness. Solving this puzzle won't just fill gaps in our simulations, it'll reveal how the universe chooses its favorites, determining which structures thrive and which fade into oblivion. And as telescopes probe deeper into the cosmic past, we might finally catch these vanishing acts in progress, watching as the Dark Ages played judge, jury, and executioner for galaxies yet to be. Neutrinos, the universe's most elusive particles, might have played puppeteer during the Dark Ages, tugging at matter with ghostly fingers too faint to feel, yet powerful enough to shape the cosmos. These subatomic wraiths, born in the infernos of the Big Bang and stellar explosions, zip through space at nearly the speed of light, barely interacting with anything. But their sheer numbers could have tipped the scales. Picture a quadrillion neutrinos streaming through every inch of space, their combined gravity subtly warping the distribution of gas and dark matter like invisible hands molding clay. The math is staggering. Even though a single neutrino has less than a millionth the mass of an electron, their staggering abundance means they could have contributed as much total mass as all the visible stars in the universe today. During the Dark Ages, when the cosmos hung in perfect balance between expansion and collapse, this neutrino sea might have created faint gravitational ripples, tiny variations in density that nudged gas into preferred paths. Over eons, these preferences amplified, guiding matter into the cosmic web's filaments and nodes. It's like sprinkling sand on a vibrating drum. The grains gather where the vibrations are weakest, tracing patterns set by unseen forces. Experiments like Ice Cube, buried deep in Antarctic ice, are hunting for relics of this neutrino influence. By detecting high-energy neutrinos from the distant universe, they're piecing together how these particles behaved in the ancient past. Some models suggest that if neutrinos had even a slight preference for certain energies or directions, they could have imprinted that bias on the large-scale structure we see today. Imagine a river carving a canyon over millennia. Neutrinos might have been the first trickle that decided where the canyon would form. But there's a twist. Not all neutrinos are created equal. The three known flavors, electron, muon, and tau neutrinos, oscillate between states as they travel. This quantum dance could have scrambled their influence during the Dark Ages, making their gravitational effects more chaotic. Some theorists argue this would have smoothed out structure, while others propose it might have created delicate subpatterns in the cosmic web, like fractal wrinkles in spacetime. The stakes: if neutrinos played a role, their fingerprints should be detectable in the clustering of galaxies or the cosmic microwave background's fine details. Future telescopes mapping millions of galaxies could reveal telltale gaps or clustering anomalies, subtle signs that ghostly particles once steered the universe's growth. And if they did, it would mean the Dark Ages weren't just shaped by the obvious giants, dark matter and gravity, but also by the universe's quietest, most abundant voyeurs, whispering to the cosmos in a language we're only beginning to decode. Some of the best evidence for how the Dark Ages ended isn't found in glowing galaxies or shimmering stars. It's hidden in the voids between them, written in the ghostly language of missing light. When quasars, those brilliant beacons powered by supermassive black holes, shine through the early universe, their light doesn't reach us unscathed. It passes through clouds of neutral hydrogen, the same fog that once blanketed the cosmos. And each time that gas absorbs a specific wavelength, the Lyman alpha line, it leaves a dark fingerprint in the quasar's spectrum. What astronomers see isn't just a few absorption lines, but an entire thicket of them, a forest so dense it reveals the universe's transition from darkness to light in exquisite detail. Think of each line in the Lyman alpha forest as a timestamp. Closer to the quasar's wavelength, the lines come from hydrogen clouds near us in the more recent universe. But as you move to shorter wavelengths blueward, each line represents gas at greater distances and thus further back in time. The astonishing part: the forest grows sparser the deeper you look, as if you're watching the fog lift in reverse. That's exactly what happened. During reionization, ultraviolet light from the first stars and galaxies blasted apart hydrogen atoms, turning them from light-absorbing neutral gas into transparent ionized plasma. The thicket of absorption lines thins out because there was less hydrogen left to block the light, a cosmic curtain being drawn back. But the forest hides more than just timing. The spacing and depth of these lines act like a cosmic barometer, revealing the temperature, density, and even the turbulence of gas during those critical years. Some lines are deep and wide, betraying dense clumps of hydrogen where galaxies were forming. Others are shallow and narrow, marking quieter regions where reionization hadn't yet reached. By mapping thousands of quasars' forests, astronomers have pieced together a patchwork timeline. Some corners of the universe cleared early, while others held onto their hydrogen fog for millions of years longer. Here's the twist: the forest might also hold clues about the very first stars. The patterns of absorption suggest that reionization didn't happen smoothly. Instead, it advanced in bubbles, like holes burning through paper at different rates. That patchiness hints at the nature of those early ionizing sources, whether they were colossal population Roman 3 stars, voracious black holes, or something even stranger. Some models even suggest the forest's faintest lines could be echoes of mini-reionization events, local bursts of starlight from tiny protogalaxies that briefly punched through the darkness before fading away. The Lyman Alpha Forest isn't just a record of the past, it's a mirror. The way light interacts with hydrogen today depends on how those atoms were arranged billions of years ago. By studying this ghostly archive, we're not just reading history, we're watching the universe learn how to shine one absorption line at a time. What if the fabric of spacetime itself was frayed during the Dark Ages, not by black holes or galaxies, but by cosmic strings, thread-like defects thinner than an atom yet stretching across the entire universe? These hypothetical relics, born from phase transitions in the early cosmos, would be scars from when the fundamental forces of nature split apart, like cracks forming in ice as it freezes. And if they existed, their ghostly gravitational pull might have sculpted the first structures in the universe, leaving trails we could still detect today. Cosmic strings aren't your average astronomical objects. They're not made of matter or energy, but are literal kinks in space-time, regions where the laws of physics twist into something unrecognizable. Picture a sweater unraveling along a single thread, except here, the thread is space-time itself, and the fray carries the mass of entire galaxies packed into an infinitely thin line. During the Dark Ages, these strings could have crisscrossed the cosmos like invisible spiderwebs, their immense gravity subtly warping the gas and dark matter around them. Wherever a string passed, it might have left behind a wake of denser material, creating preferential paths where galaxies later formed, the most tantalizing clue. Gravitational waves. If cosmic strings still exist, they wouldn't just sit quietly. Simulations suggest they'd occasionally snap or collide, sending out ripples in spacetime detectable across billions of light years. These wouldn't be the faint chirps picked up from merging black holes, but sharp, symbol crash burst signatures with no known astrophysical source. Observatories like LIGO and future space-based detectors are listening for exactly these anomalies. A single confirmed detection wouldn't just prove cosmic strings exist. It would give us a snapshot of the universe's hyperactive infancy when spacetime itself was settling into its current form. But cosmic strings could also explain some of the Dark Ages' oddest puzzles. The cold spot in the cosmic microwave background, that mysterious chilly region, might be a shadow cast by a cosmic string's gravitational lensing. The large-scale distribution of galaxies, with its puzzling filamentary voids, could reflect the paths these strings carved long before stars ignited. Even dark matter's clumping behavior might make more sense if strings acted as cosmic routers, steering invisible particles into dense knots. Of course, not all theorists are convinced. Some argue that if cosmic strings were ever common, their gravitational lensing effects should have been spotted by now. Others counter that strings could be rarer or fainter than early models predicted, hiding in plain sight. The debate hinges on observations we're only now becoming equipped to make. Next-generation telescopes mapping the cosmic microwave background in unprecedented detail, or gravitational wave detectors with broader frequency ranges could finally catch these spacetime scars in the act. Imagine the implications. Cosmic strings would be more than relics, they'd be living fossils, carrying data from the universe's first trillionth of a second encoded in their vibrations. If we find them, we're not just filling a gap in our theories, we're touching the wounds of creation itself, where spacetime first stitched itself into the cosmos we recognize today. And that discovery wouldn't just rewrite the history of the Dark Ages, it would redefine what we call reality. Supermassive black holes didn't just appear fully formed at cosmic dawn. They exploded onto the scene with impossible speed, some weighing 1 billion suns before the universe was even 1 billion years old. How could these gravitational monsters grow so fast in an era when the first stars were barely flickering to life? The answer might lie in the darkest corners of the Dark Ages, where something extraordinary skipped the usual cosmic rulebook entirely. Imagine a black hole born not from a dying star, but from the direct collapse of an entire primordial gas cloud. No supernova, no explosive death, just raw gravitational collapse on a scale never seen since. This direct collapse scenario starts with a massive, pristine cloud of hydrogen, untouched by heavy elements. Without metals to cool and fragment it, the cloud doesn't break apart into stars. Instead, it condenses into a single, unstable behemoth, collapsing so violently that it forms a black hole with tens of thousands of solar masses in one catastrophic plunge. Think of it as cosmic fast-forwarding, skipping the slow accretion process and jumping straight to the heavyweight league. The timing fits eerily well. These direct collapse seeds could have formed in rare, ultra-dense regions during the Dark Ages, lurking invisibly until the first stars ionized their surroundings. Once awakened, their immense gravity would have sucked in gas at staggering rates, outpacing even the brightest quasars. Some simulations show these black holes swallowing entire gas clouds in mere millions of years, a blink in cosmic terms explaining how they reached supermassive status so early. But the smoking gun might be hidden in the light of the most distant quasars. Their spectra show surprisingly weak traces of heavy elements, as if they grew in near-pristine environments, exactly what direct collapse predicts. If these black holes had formed from stellar remnants, their surroundings would be littered with metal-enriched debris. Instead, they act like cosmic clean freaks, hinting at origins before star pollution was widespread. Not everyone's convinced, though. Critics point out that direct collapse requires freakishly perfect conditions, gas clouds with just the right density, temperature, and lack of turbulence. Even a single nearby star's UV radiation could disrupt the process, preventing collapse. Yet supporters argue that the early universe was full of such extreme environments, especially in the dense heart of dark matter halos. The real puzzle isn't whether it happened, it's how often. Every massive galaxy today hosts a central black hole, suggesting these seeds might have been more common than we think. The implications are staggering. If direct collapse black holes existed, they didn't just wait for the Dark Ages to end. They helped end them. Their voracious feeding would have heated surrounding gas, triggering galaxy formation and flooding the cosmos with radiation. Far from passive leftovers of the first stars, these primordial giants might have been active architects of cosmic dawn, rewriting the rules of how structure emerges from darkness. And if future telescopes catch a glimpse of one forming perhaps through gravitational waves or a telltale flash of infrared light, we'll witness the birth of a titan that defied the universe's slow and steady norms. Long before water or carbon dioxide existed, before even the simplest dust grains floated in space, the universe forged its first molecule, a fragile pairing of helium and hydrogen so rare it might as well have been a ghost. Helium hydride, or He+, was born in an era when the cosmos was too hot for stable atoms, let alone bonds between them. Yet against all odds, this delicate union survived the chaos of the early universe, becoming the molecular bedrock on which all future chemistry would build. Picture the universe just 50,000 years after the Big Bang, a seething plasma so dense that electrons raced wildly between nuclei, preventing any atoms from forming. As expansion cooled the cosmos, helium nuclei, each clutching 2 protons and 2 neutrons, finally captured electrons, becoming the first stable atoms. But hydrogen, with its single proton, remained ionized longer, its electrons torn away by relentless radiation. In that narrow window of time, before hydrogen could fully reunite with its electrons, something remarkable happened. A few helium atoms drifting through the cooling plasma encountered naked hydrogen ions protons and shared their electrons in a tenuous bond. This was He+, the universe's first flirtation with molecular connection. For decades, He+, lived only in equations. Scientists knew it must have existed, but the harsh ultraviolet light of later stars should have obliterated every trace. Then, in 2019, the SOFIA Airborne Telescope caught a whisper from the past. Peering at NGC 7027, a planetary nebula 60 light-years wide, researchers spotted the molecule's infrared signature, a faint vibration at precisely 149 micrometers. This wasn't Primordial He+, but its modern descendant, proving the molecule could endure in environments mimicking the early universe's extreme conditions. The discovery was like finding a fossilized raindrop from the dawn of time. In the nebula's ultraviolet glare, helium atoms once again found themselves partnering with hydrogen ions, recreating chemistry's first dance. If He+ could form there, it confirmed theorists' models of its role in the Dark Ages. These molecules, though short-lived, acted as cosmic refrigerants, absorbing photons and cooling gas clouds just enough to let gravity gain the upper hand. Without that cooling, the first stars might have taken far longer to ignite, leaving the universe dark for additional eons, but there's a deeper mystery. Some models suggest He+ didn't just fade away, it catalyzed the formation of molecular hydrogen, H2, the fuel that powered the universe's first stars. In the shadowy depths of primordial gas clouds, a helium hydride molecule could have collided with a hydrogen atom, transferring its proton in a reaction that birthed the very first H2. This chain reaction, repeated countless times, might have filled the Dark Ages with hidden reservoirs of star fuel, waiting for gravity to strike the match. The hunt isn't over. Astronomers now scour distant quasars' absorption lines for He+'s fingerprint, hoping to catch a glimpse of it in pristine intergalactic space, untouched by later stellar pollution. If found, it would be the ultimate time capsule, a relic from the moment the universe took its first chemical breath, setting in motion the journey from simplicity to the molecular richness we see today. Every complex molecule in your body, every swirling nebula, every planet's atmosphere owes its existence to those first fragile bonds. The Dark Ages weren't just an era of darkness. They were the universe's alchemy lab, where the recipe for everything began with a whisper of helium and hydrogen clinging together against the void. While most dark matter searches focus on massive particles or hidden forces, there's a contender so ethereal it barely feels real actions. These hypothetical particles, originally dreamed up to solve a puzzle in quantum physics, might have left behind a cosmic calling card, faint radio whispers from the Dark Ages. Picture this: if actions exist, their decaying forms could have bathed the early universe in subtle radio waves, a signal so quiet it's taken decades of technological advancement just to start listening for it. Actions are unlike any traditional dark matter candidate. Where WIMP crash through detectors like invisible boulders, actions would barely interact with matter at all. Instead, they might occasionally flicker into photons in the presence of strong magnetic fields. This bizarre conversion process could leave behind a telltale hum at specific frequencies, a signature that experiments like ADMX, the Action Dark Matter experiment, are hunting in heavily shielded chambers cooled to near absolute zero. The challenge: the signal would be vanishingly weak, a single note drowned in a cacophony of cosmic static. Here's where the Dark Ages come in. During that era of perfect blackness, before stars polluted the cosmos with radiation, any photons from action decays would have traveled unimpeded across the universe. Today, their stretched-out remnants might linger as an ultra-fine radio background, a relic glow subtler than even the cosmic microwave background. Some models suggest this signal would cluster at frequencies between 50 and 500 MHz, right where FM radio broadcasts, ironically, create so much interference that detecting it requires telescopes in radio-quiet zones like Australia's outback or the South African desert. The tantalizing part: action dark matter wouldn't just solve one mystery, it could crack two. Their existence would explain why the universe's dark matter outweighs normal matter so dramatically, while also resolving a decades-old problem in particle physics called the strong CP problem, which questions why certain quantum forces behave symmetrically when they theoretically shouldn't. It's an elegant two-for-one deal that's kept physicists chasing actions despite 40 years of null results. Experiments are getting clever. ADMS uses a supercooled magnetic cavity tuned like a radio dial, scanning frequency by frequency for action clicks. Meanwhile, projects like Haystack and Organ employ quantum amplifiers to boost sensitivity, while cosmological surveys scour the sky for anomalous radio patterns. The breakthrough could come any day or never, but if it does, we won't just detect dark matter. We'll eavesdrop on the dark ages themselves, hearing the universe as it hummed to the tune of particles we're only beginning to dream of. For hundreds of millions of years, the universe didn't just sit in darkness, it sat in a deep freeze, with temperatures plummeting toward absolute zero as space expanded. Then came the cosmic defrost, a dramatic reheating event that didn't just end the dark ages, it boiled them away. The culprits, the first stars, blazing with such intense ultraviolet fury that they didn't just light up the cosmos, they fundamentally rewired it, turning a frigid hydrogen fog into a seething plasma in what scientists call the epoch of reionization. Temperature maps of the early universe tell this story in vivid detail. The cosmic microwave background shows a nearly uniform chill, just 3 degrees above absolute zero, but peer closer and subtle variations emerge. By measuring the absorption lines of distant quasars, astronomers have reconstructed how pockets of gas suddenly warmed from around -260 degrees Celsius to tens of thousands of degrees, all within a few 100 million years. That's like a glacier transforming into a supernova's shockwave in cosmic terms. The mechanism: UV photons from massive population Roman III stars, each packing enough energy to strip electrons from hydrogen atoms in a process called ionization. Here's the catch: reheating wasn't smooth or uniform. Imagine a pot of water on a stove. Some bubbles form first, then others, until the whole surface churns. Similarly, reheating advanced in localized bursts around clusters of early stars, creating ionization bubbles that grew and merged. Gas within these bubbles became transparent, allowing starlight to travel freely, while untouched regions remained shrouded in cold hydrogen. Simulations reveal a cosmic patchwork, with some areas reheating as early as 200 million years after the Big Bang, while others resisted for another half-billion years. The smoking gun lies in quasar light. When astronomers analyze spectra from quasars 12 billion light-years away, they find dense forests of hydrogen absorption lines, but only up to a certain point in cosmic time. Beyond that threshold, the forests thin dramatically, as if a great clearing had occurred. This is the moment reheating reached that region, and the pattern repeats across the sky. By mapping these transitions, researchers have traced the universe's rewiring in 3D, revealing how ionized bubbles eventually overlap to create the transparent cosmos we see today. Yet the most surprising detail: reheating didn't just change the universe's temperature, it changed its sound. In the cold, dark ages, pressure waves from the Big Bang still reverberated through the hydrogen fog, creating oscillations astronomers call baryon acoustic oscillations. As reheating ionized the gas, those waves lost their medium and froze in place. Today, their fossilized imprint shapes galaxy clustering, with galaxies preferentially separated by the distance those waves once traveled. In essence, the universe's final chill didn't just end an era, it left behind a cosmic drumbeat, still echoing in the arrangement of everything we see. Far from a passive transition, the great cosmic reheating was a violent rebirth, sculpted by the first star's harsh brilliance and those temperature maps. They're more than scientific data, they're the universe's fever chart, recording the moment it burned away its primordial shroud and stepped into the light. Buried in the faintest hum of the cosmos lies a signal unlike any other, a whisper from the dark ages encoded in hydrogen's silent song. At a wavelength of 21 centimeters, this radiation carries a story older than stars, older than galaxies, a direct line to the universe's coldest, quietest chapter. Detecting it would be like tuning into a radio broadcast from the dawn of time, but the signal is so weak that it's buried under layers of cosmic noise, terrestrial interference, and the buzz of our own technology. The magic of 21-centimeter radiation lies in hydrogen's quantum quirks. When the universe was just a sea of neutral hydrogen, the protons and electrons in these atoms occasionally flipped their spins relative to one another, releasing a photon with that exact wavelength. In today's universe, this process is drowned out by brighter sources, but during the Dark Ages, before stars and galaxies flooded space with light, it was the only emission. The intensity and frequency of this signal would reveal the temperature, density, and even the velocity of hydrogen gas back then, painting a 3D map of the cosmos in its infancy. Then came EDGES, the experiment to detect the global epoch of reionization signature. In 2018, this small ground-based radio antenna in the Australian outback reported a stunning claim. It had detected the 21-centimeter signal from the Dark Ages, a dip in the radio spectrum corresponding to hydrogen-absorbing cosmic background radiation around 180 million years after the Big Bang. The finding sent shockwaves through cosmology if confirmed. It would be the earliest direct glimpse of the pre-stellar universe ever captured, but controversy erupted almost immediately. The signal was twice as strong as theoretical predictions, suggesting hydrogen in the early universe was far colder than anyone imagined. Theorists scrambled to explain it, proposing exotic possibilities like interactions between dark matter and normal matter that siphoned away heat, or even primordial black holes cooling the gas. Skeptics, however, pointed to potential flaws, terrestrial interference, calibration errors, or unaccounted for radio emissions from the Milky Way. The debate rages on, with follow-up experiments like Sarah's and LEDA failing to replicate EDGES results conclusively. What's at stake isn't just a technical disagreement. If EDGES is right, we're staring at evidence of physics beyond the standard model, a cosmic anomaly that could redefine our understanding of dark matter or the early universe's thermodynamics. If it's wrong, the hunt for 21-centimeter radiation becomes even more urgent, pushing engineers to design ever more sensitive arrays in radio-quiet zones from the Chilean deserts to the far side of the Moon. The next generation of telescopes, like the Square Kilometre Array, promises to settle the debate. With thousands of antennas spanning continents, SKA could map the 21-centimeter signal in unprecedented detail, transforming it from a faint dip in a graph to a rich cosmic tapestry. Imagine seeing the Dark Ages not as a vague era, but as a dynamic period where hydrogen flowed like rivers in the void, sculpted by forces we've yet to name. For now, EDGES' signal remains a tantalizing maybe, a ghost in the data that could vanish under scrutiny or unlock secrets buried for 13 billion years. Either way, the chase for hydrogen's echo reminds us that the universe's oldest light isn't always the brightest. Sometimes it's the quietest signals that hold the loudest truths. The Dark Ages might hold more than just our universe's secrets. They could be a window into realities beyond our own. Imagine a moment just after the Big Bang when the fabric of space-time was still frothing with quantum energy, a seething chaos where the laws of physics hadn't yet settled into their final form. In that white-hot frenzy, some theories suggest our universe wasn't alone. Bubble universes, countless other cosmic domains, each with their own unique physics, might have sprouted alongside ours, brushing against it before drifting away into their own dimensions. And if they did, those fleeting encounters could have left faint scars in the Dark Ages, imprints hidden in the cosmic microwave background or the distribution of galaxies. One clue lies in the cold spot, that eerie chill in the CMB that defies conventional explanations. While some scientists blame cosmic voids or exotic dark energy, others propose something even wilder, that it's the bruise of a long-ago collision with another universe. Picture two soap bubbles grazing each other in a sink. The spot where they meet would distort slightly, leaving a subtle dimple. If our infant universe bumped into a neighboring bubble during the Dark Ages, the gravitational shockwave could have created a vast, cold region in the CMB, a fossilized fingerprint of contact with an alien cosmos. But collisions aren't the only way parallel realities might have whispered to us. Quantum tunneling, the bizarre phenomenon where particles cheat physics by teleporting through barriers, could have allowed energy or information to leak between universes during the Dark Ages. In the bizarre quantum foam of the early cosmos, space-time itself might have been porous enough for brief connections to form. These quantum handshakes could have subtly altered the distribution of matter in our universe, skewing the formation of the first galaxies in ways that linger today. Some simulations even suggest that if such tunneling happened, it would create telltale asymmetries in the large-scale structure of the cosmos, like a mirror cracked just slightly out of alignment. Then there's the multiverse's ultimate sleight of hand, infinite variations. If eternal inflation, the theory that our universe is just one of countless bubbles in an ever-expanding multiverse, is real, then every possible version of physical laws exists somewhere. That means certain anomalies in the Dark Ages, like regions where hydrogen reionized unusually fast or slow, might not be random flukes. They could be echoes of nearby universes where the strength of gravity, the mass of neutrinos, or even the nature of dark energy are subtly different, warping the boundary between realities. Of course, not all physicists are convinced. Critics argue that without direct evidence, multiverse theories border on metaphysics. But supporters counter that the Dark Ages offer something rare, a pristine laboratory, untouched by later cosmic clutter, where even the faintest fingerprints of other realities might survive. Future telescopes mapping the CMB with nanometer precision or analyzing the hydrogen absorption lines of ancient quasars could stumble upon irregularities that defy all local explanations. And if they do, the answer might not lie in our universe at all, but in the infinite array of possibilities just beyond the veil of space-time. The thought is humbling. The Dark Ages, long dismissed as a featureless void, might be the universe's most delicate parchment, a place where other worlds, other physics, even other versions of ourselves left their mark. If we ever learn to read those whispers, we won't just uncover our own origins. We'll glimpse the unimaginable vastness of everything else. Black holes aren't just cosmic vacuum cleaners, they might have been atomic bombs in the Dark Ages, detonating with such force that their echoes still ripple across the universe today. The key lies in an obscure but explosive phenomenon called superradiance, where a spinning black hole's sheer rotational energy gets amplified into a runaway chain reaction, unleashing a blast of particles and radiation so powerful it could have rewritten entire chapters of cosmic history. Picture a black hole spinning near the speed of light, dragging spacetime itself into a whirlpool around it. If just the right kind of particle, like an action or photon, gets caught in this gravitational vortex, it doesn't get swallowed. Instead, it steals energy from the black hole's spin, bouncing back and forth between the event horizon and an invisible boundary called the ergosphere. With each pass, the particle gains strength, multiplying until the system can't contain it anymore. The result, a catastrophic explosion orders of magnitude brighter than a supernova, a black hole bomb detonating in the void. Now imagine this happening not in today's universe, but during the Dark Ages when the cosmos was a silent, gaseous fog. Primordial black holes, relics of the Big Bang's chaos, would have been the perfect candidates, small enough to spin wildly, yet massive enough to trigger superradiant explosions. Each blast would have punched through the surrounding hydrogen, ionizing vast bubbles of gas and flooding space with high-energy radiation. This could explain some of the patchy reionization patterns we see in the cosmic microwave background, bright spots where black hole bombs went off like strings of firecrackers, jump-starting star formation in their wake long before the first galaxies fully formed. But here's where it gets eerie. Fast radio bursts, those mysterious millisecond-long blips of radio energy detected across billions of light years, might actually be the distant echoes of these ancient explosions. Some FRBs repeat in rhythmic patterns, matching the predicted aftermath of superradiant instabilities. If true, we're not just seeing random cosmic static, we're catching the final whispers of black holes that self-destructed in the Dark Ages, their shockwaves stretched and diluted over eons into the faint signals we detect today. Critics argue that superradiance requires impossibly fine-tuned conditions, black holes spinning at precise rates, surrounded by clouds of just the right particles. Yet supporters point to the sheer weirdness of FRBs and the gaps in our reionization timeline as evidence that something extreme was happening back then. Whether these explosions were rare flukes or cosmic constants, their legacy might be written in the scars they left on the universe's hydrogen fog and the ghostly radio bursts that still haunt the dark between galaxies. If black holes really did bomb the Dark Ages into submission, they weren't just destroyers, they were unwilling midwives, forcing the universe out of darkness with blasts of raw, apocalyptic energy. Time might not have ticked the same way during the Dark Ages, not because some cosmic clock ran slower, but because gravity itself warped the very fabric of reality. Einstein taught us that time isn't absolute, it stretches and compresses under extreme conditions, and in the early universe, conditions didn't get much more extreme. Picture a cosmos so dense that matter was packed tighter than the core of a neutron star, where the gravitational pull of every particle tugged at spacetime like weights on a rubber sheet. In that primordial crush, seconds for us might have dragged like hours back then. Or worse, entire cosmic epochs could have flickered by in what we'd perceive as an instant. This isn't just philosophical musing. The math holds up. General relativity predicts that time dilation would have been rampant in the early universe's ultra-dense regions. Gas clouds on the verge of collapsing into stars might have experienced time so differently from their surroundings that their own dynamics played out in a bizarre slow motion. Imagine watching a raindrop fall through molasses. What looks like a single event to us could have been a drawn-out drama for the particles involved. The implications are staggering. If time flowed unevenly during the Dark Ages, our telescopes might be seeing some events in the wrong sequence, like cosmic film strips spliced out of order. Here's where it gets even stranger. Some theories suggest that dark matter, that invisible scaffolding of the cosmos, could have created localized pockets where time practically stood still. In regions where dark matter clustered most densely, its gravitational grip might have slowed time to a crawl, effectively putting those areas on cosmic pause while the rest of the universe raced ahead. This could explain puzzling observations, like why certain ancient galaxies appear too mature for their age. Their stars might have formed in slow-motion nurseries, aging faster relative to the broader universe. But how would we even detect this? The smoking gun could lie in the cosmic microwave background's fine-grained patterns. If time dilation warped the universe's early acoustic oscillations, those primordial pressure waves from the Big Bang, it might have left subtle asymmetries in the CMB's hot and cold spots. Future telescopes like the next-generation CMB S4 experiment aim to hunt for these anomalies, searching for telltale smudges in the afterglow of creation that betray where time itself stuttered. The wildest possibility, time's erratic flow might still be echoing today. Gravitational waves from mergers of primordial black holes could carry traces of time dilation in their waveforms, stretched or compressed by the extreme gravity of their birthplaces. If we catch these ripples with enough precision, they could serve as cosmic stopwatches, revealing how time bent in the Dark Ages. So when we peer into deep space and see the universe as it once was, we're not just looking across distance, we're peering into a realm where time itself was pliable, where the rules we take for granted twisted into something alien. The Dark Ages weren't just a gap in light. They might have been a wrinkle in time, a chapter written in ink that faded and bled at its own unpredictable pace. And if we learn to read those distortions, we'll uncover more than the universe's history. We'll decipher the tempo of its infancy, the rhythm of existence itself. The Dark Ages may have hosted an invisible cosmic doppelganger matter that mirrored our own in every way, yet remained forever out of reach. This mirror matter theory proposes an entire shadow universe of particles interacting only through gravity, a phantom twin to the atoms and light we know. While today this elusive substance would blend seamlessly into dark matter's mysteries, during the universe's formative years, its gravitational tugs could have orchestrated the collapse of the first structures in ways we're only beginning to unravel. Imagine two parallel sheets of paper hovering millimeters apart, close enough to bend toward each other, yet never touching. That's how mirror matter might have coexisted with normal matter in the early cosmos. Each proton, electron, or hydrogen atom in our universe would have had a counterpart in this shadow realm, identical in mass but deaf to electromagnetism and the nuclear forces that shape our reality. During the Dark Ages, these phantom particles would have clustered under gravity's pull just like ordinary matter, creating invisible scaffolding that accelerated galaxy formation in our visible universe. The eerie part, their gravitational whispers might explain why some proto-galaxies formed faster than standard models predict, as if unseen hands were guiding cosmic assembly behind the scenes. The smoking gun could lie in cosmic dawn's timing. If mirror matter existed, its early influence would have left subtle fingerprints, perhaps regions where reionization happened suspiciously early, fueled by extra gravitational collapse from these hidden counterparts. Some simulations suggest mirror matter would have created echo density waves in the primordial plasma, faint ripples that nudged hydrogen clouds into alignment long before stars ignited. Astronomers hunting for anomalies in the cosmic microwave background's polarization patterns might already have glimpsed these ghostly interventions without realizing it. But mirror matter isn't the only exotic contender. Another candidate, neutral naturalness, proposes particles that split the difference between dark and ordinary matter, interacting weakly but detectably through forgotten forces. These would have acted like cosmic moderators during the Dark Ages, slowing star formation in some areas while accelerating it in others. The result, a patchwork quilt of ionization bubbles unlike anything predicted by conventional physics. Critics argue these theories stretch Occam's razor to the breaking point. Yet supporters counter that the universe owes no debt to simplicity, especially when faced with puzzles like the missing satellite galaxies or the universe's puzzlingly smooth large-scale structure. If future telescopes detect gravitational lensing anomalies around ancient gas clouds or odd vibrations in the cosmic web's filaments, we might finally spot the phantom's shadow. What's at stake isn't just another dark matter model. If mirror matter or its kin shaped the Dark Ages, they didn't just hide in the darkness. They built in it, sculpting the foundations of everything we see today from behind a veil we're only now learning to pierce. The next great cosmic revelation might not come from what we observe, but from what we realize has been beside us all along, silent, unseen, and utterly essential. Buried in the faint static of the cosmos is a whisper so ancient, it predates even the cosmic microwave background, the ghostly echo of the universe's first neutrinos. These subatomic phantoms, born in the unimaginable heat of the Big Bang, have streamed untouched through space for over 13 billion years, carrying secrets from the universe's very first second. If we could catch just a handful of these relic neutrinos, they'd rewrite the entire story of the Dark Ages, revealing details no telescope or simulation could ever glimpse. The cosmic neutrino background is the ultimate time capsule. While the CMB shows us the universe at 380,000 years old, These neutrinos offer a snapshot from 1 second after creation, a time when the cosmos was still a seething plasma of particles too energetic to form atoms. Unlike photons, which scattered endlessly in the early universe's thick soup, neutrinos barely interact with matter. Once they decoupled from the chaos, they flew straight and true, their trajectories unaltered by stars, galaxies, or even black holes. Detecting them would be like finding a pristine letter from the Big Bang itself, unopened and unedited by time. The challenge: these neutrinos are absurdly elusive. With energies a billion times lower than those from the Sun, they slip through entire planets like ghosts through walls. To catch them, scientists are turning to projects like Ptolemy, a Princeton-based experiment using ultra-cold graphene sheets and radioactive tritium to intercept these cosmic relics. The idea is audacious. When a relic neutrino collides with a tritium nucleus, it could trigger a minuscule but measurable energy spike. Ptolemy detectors, chilled to near absolute zero and shielded from all other radiation, are fine-tuned to spot that needle in a haystack. But why go to such extremes? Because these neutrinos could answer one of the Dark Age's biggest mysteries: how matter clumped into galaxies so quickly. Neutrinos from the Big Bang move at near light speed, creating a subtle pressure that would have smoothed out small-scale density fluctuations in the early universe. By measuring their exact energy and distribution, we could finally understand why galaxies formed where they did, and whether dark matter's gravity had an invisible dance partner in shaping the cosmos. There's another twist. If neutrinos have even a tiny intrinsic mass, a property still hotly debated, their collective gravity could have warped space-time during the Dark Ages in ways we've never accounted for. Some models suggest this might explain anomalies in the CMB's large-scale structure, like why certain regions of space seem slightly over or under-dense compared to predictions. It's as if the universe's blueprint was drawn with a shaky hand, and neutrinos might be the reason why. The hunt isn't just technical, it's poetic. These neutrinos are the last untouched messengers from the universe's birth, and their stories are written in a language we're only beginning to decode. If Ptolemy or its successors succeed, we won't just be observing the Dark Ages. We'll be touching the very first second of time, feeling the pulse of creation before light itself had room to shine. And in that moment, the darkest chapter of cosmic history might finally step into the light. What if the entire universe during the Dark Ages wasn't three-dimensional at all, but a hologram, a cosmic projection flickering on the surface of some unfathomable distant boundary? It sounds like science fiction, but this holographic principle, born from string theory's most radical ideas, might explain some of the era's deepest mysteries. Imagine reality as a cosmic movie screen, with all the richness we perceive: the swirl of galaxies, the glow of stars being nothing more than shadows cast by information encoded on the edge of existence. During the Dark Ages, when space-time itself was simpler and more compressed, these holographic rules might have left fingerprints we can still detect today. The math behind this is dizzying. In a holographic universe, the information needed to describe everything inside a region of space, every particle, every force, could theoretically fit on its two-dimensional surface. It's like storing an entire 3D film on a flat DVD. During the Dark Ages, when the cosmos was smaller and denser, this encoding might have been more apparent. Quantum fluctuations that normally fade into the background could have projected distortions visible in the cosmic microwave background, strange patterns or anomalies that resist conventional explanations. Some theorists even suggest that the cold spot, that enigmatic chill in the CMB, might not be a void at all, but a glitch in the cosmic projection, a place where the universe's source code hiccuped during decompression. But how would this affect the Dark Ages specifically? Picture the early universe as a cosmic hard drive nearing capacity. As matter and energy compressed in the dense young cosmos, information storage might have reached fundamental limits, forcing reality to compress data in holographic ways. This could have altered how gravity worked on quantum scales, subtly changing how the first gas clouds collapsed. If true, we wouldn't just find clues in the CMB. Ancient hydrogen clouds might show odd clustering patterns, as if their formation followed rules written in fewer dimensions than we're used to. The most tantalizing evidence comes from black holes. The holographic principle predicts that all the information swallowed by a black hole gets smeared across its event horizon like data on a hard drive surface. If primordial black holes littered the dark ages, their holographic disks might have imprinted unexpected signatures in the surrounding gas, creating regions where matter behaved like pixels in a low-resolution image. Future radio telescopes mapping the distribution of hydrogen from that era could stumble upon these pixelated patches, areas where structure appears oddly digital, as if the universe hadn't yet rendered in full 3D. Of course, skeptics argue that holography's fingerprints would be too subtle to distinguish from standard cosmic variants. Yet supporters counter that the Dark Ages offer a unique testing ground precisely because they were so pristine, free of later stellar pollution that could mask these primordial signals. If we ever detect anomalies that defy conventional physics, like hydrogen clouds rotating in mathematically impossible ways or CMB patterns that match holographic projections rather than inflation's predictions, we might be staring at reality's true nature. The implications are staggering. If the universe was holographic during the Dark Ages, it might still be now. We just inhabit a higher resolution version of the same projection. Every galaxy, every atom, even the void between stars, could be nothing more than an elaborate illusion, data decoded on the fly from some distant cosmic boundary. The Dark Ages wouldn't just be a chapter in cosmic history. They'd be the universe's debug mode, a time when the underlying code was still visible before the simulation rendered itself into the richness we take for granted. And if that's true, decoding those anomalies wouldn't just solve a cosmic mystery. It would reveal the very fabric of reality itself. The universe has a missing matter problem, and no, we're not talking about dark matter. This time, it's the ordinary stuff, the baryons that make up stars, planets, and even us. According to the cosmic ledger, about half of this normal matter has gone unaccounted for since the Dark Ages. The numbers don't lie. If you tally up all the visible matter in galaxies and gas clouds today, it adds up to barely half of what the Big Bang's afterglow tells us should be there. So where did the rest go? The answer might lie in a shadowy cosmic web of superheated filaments, a place so diffuse and faint we've only just begun to trace its outlines, the warm-hot intergalactic medium, or WIM. Picture the universe not as a collection of glittering galaxies, but as a vast, interconnected network of rivers so thin and transparent they're almost invisible. The WIM is exactly that, a sprawling system of ionized gas filaments threading between galaxies like ghostly highways. These tendrils of matter are so hot, between 100,000 and 10 million degrees, that they glow not in visible light, but in far more elusive X-rays and ultraviolet. And they're so diffuse that a single cubic meter of this gas might contain just a single atom. That's why we've missed it for so long. Unlike stars or nebulas, the WIM doesn't announce itself with brilliant displays. It's the universe's whisper, a background hum drowned out by louder cosmic voices. But how did half the universe's matter end up hiding in these nearly invisible threads? The Dark Ages hold the key. During that era, gravity was already pulling gas into the cosmic web's filaments, but without stars or galaxies to ionize and heat it, most of this gas remained too cool to detect. As the first stars ignited and reionization began, their UV radiation and supernova shockwaves blasted this gas, superheating it until it became the WIM we now struggle to see. By the time galaxies lit up in earnest, the WIM was already the universe's largest reservoir of normal matter, a cosmic attic stuffed with the leftovers of creation. The hunt for this missing matter is like mapping a city using only the shadows of its power lines. Astronomers have turned to quasars, those brilliant beacons of the early universe, whose light pierces through the WIM filaments on its way to us. Every time that light passes through a filament, highly ionized oxygen and other trace elements in the WIM absorb specific wavelengths, leaving faint absorption lines in the quasar spectrum. It's the universe's version of reading tea leaves, interpreting the patterns of missing light to reconstruct the structure of something we can't directly see. The stakes: if the WIM accounts for the missing baryons, it completes our cosmic inventory, shutting the book on one of astronomy's greatest puzzles. But if not, we're back to square one, forced to consider even wilder possibilities like matter leaking into extra dimensions or transforming into exotic particles during the Dark Ages. For now, the WIM remains the prime suspect, a shadowy network that might finally explain where the universe stashed half of itself. And as X-ray telescopes grow more sensitive, we're on the verge of turning these faint whispers into a roar, finally illuminating the hidden architecture that's been there all along, woven into the darkness between the stars. During the Dark Ages, the fabric of spacetime itself might not have been smooth and serene. It could have been a seething, bubbling quantum foam, writhing with microscopic fluctuations on scales a billion times smaller than an atom. Picture the universe not as an empty stage, but as an ocean during a storm, with waves and whirlpools constantly forming and dissolving at the smallest possible level. These weren't just random jitters, they were the universe's fundamental structure, revealing its true, chaotic nature. And in this frenzied sea, light attempting to traverse the cosmos wouldn't have traveled in straight, pristine lines. It would have wobbled, scattered, and twisted as it moved through the froth. This idea isn't pure speculation. It emerges from cutting-edge theories of quantum gravity, which attempt to reconcile Einstein's relativity with the bizarre rules of quantum mechanics. In most models, spacetime below a certain scale isn't continuous but granular, like a digital image zoomed in until you see the individual pixels. During the Dark Ages, when the universe was denser and more energetic, this quantum foam could have been significantly more turbulent, creating tiny fluctuations in the path of any light trying to pass through. Imagine trying to send a laser beam through a fog so thick that every photon gets jostled unpredictably, except instead of fog, it's spacetime itself that's foamy and unstable. The wildest implication: this frothiness might have left traces in the cosmic microwave background. If light from the early universe had to navigate this quantum turbulence, its journey could have imprinted subtle distortions in the CMB's polarization patterns, odd swirls or unexpected smudges that don't fit standard models. Some researchers argue that anomalies like the infamous axis of evil, a mysterious alignment of hot and cold spots in the CMB that defies randomness, might actually be artifacts of spacetime's quantum nature during the Dark Ages. It's as if the universe's baby photos were taken through a frosted lens, one that warped the image in ways we're only now learning to decode. But the quantum foam doesn't just affect light. If spacetime was truly churning at microscopic scales, it could have influenced how matter itself behaved. Dark matter might have clumped differently under these conditions, forming structures faster or slower depending on how the foam's fluctuations interacted with gravity. Even the expansion of the universe could have been subtly altered, with pockets of quantum turbulence briefly accelerating or slowing cosmic growth in ways that left lasting wrinkles in the large-scale structure we see today. The challenge, of course, is testing this. Quantum foam operates at scales far beyond our current experimental reach, the Planck length, a distance so tiny that probing it would require particle accelerators the size of galaxies. Yet indirect evidence might still be hiding in plain sight. Gravitational wave observatories like LIGO or the future LISA mission could detect minute anomalies in the ripples from merging black holes, hints that spacetime's texture isn't perfectly smooth but faintly corrugated even now. Alternatively, ultra-precise measurements of distant quasars might reveal that their light arrives with tiny, unexplained delays, as if it had to navigate an invisible froth on its journey across the cosmos. What's astonishing is that this quantum turmoil wouldn't have been a sideshow, it might have been the main event. The Dark Ages weren't just a quiet prelude to cosmic dawn. They were an era where the universe's most fundamental layer was still raw and unsettled, where space-time itself hadn't yet hardened into the smooth continuum we take for granted. If these theories hold, then every galaxy, every star, every atom we see today was shaped not just by gravity and light, but by the ghostly turbulence of a quantum sea we're only beginning to fathom. And as we peer deeper into that ancient darkness, we might finally catch a glimpse of the froth from which reality itself emerged. The very first black holes might have cheated the cosmic life cycle entirely, forming not from the explosive deaths of stars, but from raw, unfiltered collapse on scales that dwarf anything in the modern universe. Picture this, a vast cloud of pristine hydrogen gas, untouched by the heavy elements that stars later forged, hovering in the darkness of the early cosmos. Under normal circumstances, such a cloud would fragment into countless smaller clumps, birthing a cluster of stars. But in the dense, chaotic conditions of the Dark Ages, some of these clouds may have bucked the rules entirely, collapsing in one uninterrupted freefall directly into black holes with no stellar middleman whatsoever. This direct collapse scenario rewrites our understanding of black hole origins. Instead of requiring a massive star to exhaust its nuclear fuel and implode under its own gravity, these primordial behemoths would have formed when entire gas clouds stretching hundreds of light-years across succumbed to gravity's pull without ever igniting fusion. The key ingredient, a lack of heavy elements, modern gas clouds laced with carbon and oxygen can cool efficiently by radiating away heat, allowing them to fragment into star-sized pieces. But in the early universe, where only hydrogen and helium existed, gas couldn't cool fast enough to break apart. The result, a catastrophic, monolithic collapse straight into a black hole's event horizon, with masses tens of thousands of times that of our Sun, all in one roaring, unfragmented plunge. The implications are staggering. These direct collapse black holes wouldn't just be oddities, they'd be the missing seeds for the supermassive monsters we find at the hearts of galaxies today. Observations of quasars shining less than 1 billion years after the Big Bang reveal black holes already weighing billions of solar masses. Traditional formation models struggle to explain how they grew so fast. But if they started as direct collapse behemoths, their head start makes perfect sense. Imagine planting a sapling versus a full-grown tree. The latter doesn't need centuries to dominate the forest. Supporting this theory are the strange properties of some early quasars. Their light spectra show surprisingly low metal content, as if they formed in environments where stars had barely begun polluting space with heavy elements. This aligns eerily well with direct collapse, which requires metal-free gas to prevent fragmentation. It's like finding a pristine, unpainted canvas in an artist's studio, evidence that the quasar's birthplace skipped the usual stellar chaos entirely. Yet mysteries remain. Direct collapse demands near-perfect conditions, gas clouds with just the right density, angular momentum, and shielding from disruptive radiation. Too much turbulence and the cloud fragments into stars. Too little shielding and nearby starlight heats the gas, preventing collapse. Some theorists argue these conditions were vanishingly rare, while others counter that the early universe was a carnival of extremes, with pockets of unnatural stillness where gas could collapse undisturbed. The hunt for proof is on. Astronomers scour distant quasars for chemical signatures that betray their origins, while simulations recreate the knife-edge physics of primordial gas collapse. If we're right, these black holes weren't just inhabitants of the Dark Ages, they were its architects, sculpting the first galaxies with their gravity and flooding the cosmos with radiation that helped end the darkness. And if next-generation telescopes catch a whiff of their formation, perhaps through gravitational waves or the flash of infalling gas, we'll witness a cosmic shortcut so audacious, it rewrites the rules of how monsters are born. The early universe wasn't just a silent void, it was ringing like a colossal bell, its deepest tones still echoing in the arrangement of galaxies today. These aren't mere metaphors. Baryon acoustic oscillations, or BAO, are physics' version of fossilized sound waves, imprinted in the cosmos during its fiery infancy and frozen into the cosmic web during the Dark Ages. Picture the universe's first 500,000 years, a seething plasma so dense that photons and particles were locked in a violent tug of war. Gravity pulled matter inward, while radiation pressure from the blistering heat pushed outward, creating rhythmic compressions and rarefaction sound waves propagating through the cosmic soup at half the speed of light. When the universe cooled enough for atoms to form, releasing photons in what we now see as the cosmic microwave background, those sound waves abruptly stopped, leaving behind spherical ripples where matter had been pushed outward. Like a record pressed into space-time itself, these ripples became the universe's default spacing for structure. Over billions of years, galaxies preferentially formed along the crests of these ancient waves, creating a predictable pattern. Clusters separated by roughly 500 million light-years, a cosmic fingerprint of that primordial rhythm. The eerie part, we can still hear the echoes. Modern galaxy surveys like the Sloan Digital Sky Survey reveal this signature in stunning detail, millions of galaxies clustering at intervals that match the BAO scale with uncanny precision. It's as if the universe's first note became its architectural blueprint, with voids and filaments aligning to a score written before stars even existed. But the Dark Ages added a twist. During that era, while visible light couldn't travel far, these density ripples continued evolving under the quiet influence of dark matter's gravity. The waves didn't just freeze, they stretched as the universe expanded, their wavelengths lengthening like a record played at the wrong speed. By the time the first stars reignited the cosmos, the BAO scale had doubled, leaving behind a ruler etched in space-time that astronomers now use to measure cosmic expansion itself. What's astonishing is how cleanly these oscillations survived the Dark Ages blackout. Unlike later structures warped by supernova and galactic collisions, BAOs remained pristine, their geometry untouched by stellar chaos. They're the universe's most reliable yardstick, a tuning fork struck at the dawn of time, still vibrating faintly in the darkness between galaxies. Future telescopes like the Dark Energy Spectroscopic Instrument aim to map millions more galaxies, refining our measurements of these oscillations to within 1% accuracy. If they succeed, we won't just trace the universe's expansion, we'll decode the exact pitch of its first and oldest song, a melody that began in fire, lingered in silence, and now hums softly beneath the night sky. The vacuum of space isn't just empty, it's a simmering quantum field, thrumming with potential energy that dictates the very laws of physics. But what if that vacuum isn't as stable as we think? Beneath the apparent stillness of the Dark Ages, the universe might have been teetering on the edge of catastrophe, its fundamental state a precarious illusion. This is the nightmare scenario of the false vacuum, a metastable reality that could have collapsed at any moment, rewriting existence itself in a wave of annihilation. Picture the early cosmos as a marble balanced on the tip of a mountain. The marble represents our vacuum state, the arrangement of quantum fields that make particles behave the way they do. It seems stable, but there's a lower valley somewhere below, a true vacuum where those fields could settle with far less energy. All it would take is one quantum nudge, a random fluctuation, a high-energy collision, to send the marble tumbling, triggering a bubble of true vacuum that expands at light speed, erasing every law of physics in its path. The chilling part, if this bubble had formed during the Dark Ages, we'd never know. The entire universe, stars, galaxies, even space-time itself, would have vanished before the first light could escape. The math behind this is unnervingly plausible. Quantum field theory allows for metastable vacua, and some models of cosmic inflation suggest our universe might still be in one. During the Dark Ages, before the first stars lit the fuse of complexity, the conditions were ripe for such a collapse. Energy densities were higher, quantum fluctuations more violent. A single random event, like a primordial black hole evaporating or a region of space tunneling through a quantum barrier, could have spawned a deadly bubble. Some theorists argue the only reason we're here to ponder this is sheer luck. The Dark Ages lasted long enough for the universe to cool into relative safety, like a bomb that didn't detonate simply because its timer was set too long. Evidence for this cosmic sword of Damocles might lurk in the cosmic microwave background. If a vacuum collapse bubble almost formed during the Dark Ages, its gravitational shadow could have left faint circular anomalies in the sim regions where temperature fluctuations align in unnatural rings. Astronomers have searched for these patterns, though none have been confirmed. Another clue could come from high-energy particle collisions. If our vacuum is metastable, experiments like the Large Hadron Collider might detect particles behaving slightly differently at extreme energies, hinting at the deeper valley waiting beneath our feet. The most mind-bending possibility, the Dark Ages might not have been the universe's first vacuum transition. If eternal inflation theory is correct, our entire cosmos could be the aftermath of a previous bubble's expansion, one in an endless chain of universes, each with different physics. In this view, the Dark Ages were merely the calm between storms, a fleeting pause before the next roll of the quantum dice. What stops us from dismissing this as speculative fiction is the stakes. A false vacuum collapse isn't just a reshuffling of particles, it's a total rewrite of reality's rulebook. The speed of light, the strength of gravity, even the existence of atoms could be erased in an instant. The fact that we exist to debate this might be the only proof we'll ever get that the Dark Ages' silence wasn't a prelude to oblivion, but the universe holding its breath and choosing against all odds to exhale. What if the Dark Ages weren't just a cosmic phase but a glitch in the system? The simulation hypothesis, that mind-bending idea that our universe might be an advanced digital construct, offers a wild twist on this ancient era. Think of it like this: in a simulated reality, rendering an entire universe in real time would demand insane computational power. So what if the Dark Ages were the universe's low-power mode? A stretch where the simulation dialed down detail to save resources. No stars, no galaxies, just the bare minimum physics ticking over until more processing power could be allocated to light up the fully immersive cosmic experience we see today. The elegance of this idea lies in its parallels with modern gaming. When a game engine can't render every detail at once, it uses fog, darkness, or simplified physics to hide distant areas until the player gets closer, a trick called level of detail optimization. The Dark Ages could be the ultimate example of this, a placeholder era where the simulation deferred complex calculations like star formation and galactic evolution until the player, conscious observers like us, were ready to perceive them. The moment the first stars ignited, that might have been the universe's graphics card finally kicking into high gear, but here's where it gets even stranger. The simulation argument could explain some of the Dark Ages' odd quirks. Take the missing dwarf galaxies problem, why we see fewer small galaxies than simulations predict. In a rendered universe, distant or minor objects might be approximated or culled entirely to save memory, just like how video games simplify background scenery. Or consider the universe's startling uniformity. The cosmic microwave background's near-perfect symmetry has long puzzled scientists, but if the early universe was running on baseline procedural generation, with higher resolution details added only as needed, that sameness starts to make eerie sense. Critics might dismiss this as speculative fun, but even serious physicists entertain the simulation hypothesis as a legitimate thought experiment. The late cosmologist John Barrow once suggested that if our universe is simulated, we might find evidence in subtle rounding errors, places where energy or angles don't quite add up perfectly. The Dark Ages, with their sparse, uncluttered conditions, could be the ideal place to spot such artifacts. Imagine discovering that the universe's initial density fluctuations follow a mathematical pattern too clean to be random, like the repeating textures in a video game world. Of course, there's a delicious irony here. Our best tools for probing the Dark Ages supercomputers running cosmic simulations might inadvertently mirror the very process we're theorizing about. Every time astrophysicists model the early universe with limited computing power, they're forced to simplify physics in ways hauntingly similar to the rendering limits idea. It's as if we're reverse engineering the universe's source code by recreating its constraints. Whether you buy the simulation angle or not, it reframes the Dark Ages in a thrilling new light. They weren't just an empty chapter, they were a canvas waiting for the brushstrokes of complexity, whether painted by natural physics or some unfathomable cosmic programmer. And if we ever find evidence that reality has a settings menu, those long eons of darkness might be where the debug logs are hidden. From primordial black holes forming cosmic scaffolding to parallel universes leaving bruises in the CMB, the Dark Ages were anything but empty. We've explored exotic dark matter bending the rules of gravity, quantum foam churning beneath the surface of reality, and even the spine-chilling possibility that our universe balanced on a knife's edge between existence and annihilation. But here's the thrilling part: we're not just theorizing in the dark anymore. The James Webb Space Telescope is already peeling back layers of cosmic history, capturing light from the universe's first galaxies with staggering clarity. Every infrared photon it collects carries whispers from that shadowy epoch, hinting at which theories might crack under scrutiny and which could rewrite physics itself. Next-generation observatories like the Square Kilometre Array will take us even further, tuning into the 21-centimeter hum of ancient hydrogen like a cosmic time machine. Imagine mapping the Dark Ages in 3D, watching ionization bubbles form in real time across billions of light years. Or picture gravitational wave detectors snagging ripples from colliding primordial black holes, confirming whether they truly seeded the galaxies we see today. Even wilder possibilities loom. Action hunting experiments could unveil dark matter's identity, while quantum gravity probes might catch spacetime's pixelated secrets. But the greatest discoveries won't just belong to scientists. Every viewer staring at these cosmic puzzles brings fresh perspective. Maybe you're captivated by the holographic universe's coded depths, or the eerie elegance of mirror matter shaping existence from the shadows. Perhaps the simulation hypothesis's cosmic loading screen sparks your imagination, or the thought of vacuum decay keeps you up at night. That's the beauty of the unknown. It invites us all to question, wonder, and connect. So tell us, which theory makes your mind race? Drop your thoughts below, and let's keep unraveling the universe's oldest mysteries together. The next breakthrough might just start with your curiosity.